Hi everyone, my name is Elijah Perrier, and this is my talk today for AGI 2026 on What's Per Intelligence Part 2, Algorithmic Catalysis, and apologies I'm not able to be there. Um, so this talk today is about uh, dealing with this issue that we're facing towards AGI, which is we need energy efficient intelligence. The race to build intelligent systems is facing the realities of physics. Scaling intelligence by brute force is becoming increasingly expensive. More intelligence currently means more computation, and more computation means more energy, cooling, and cost. And so, the future of AGI, I argue, needs new principles for energy efficient intelligence, not simply larger models. So, the question is what lets a system solve intelligent tasks using less physical work? In earlier work of mine, I provide a way to try to observe and measure this. It's called watts per intelligence. It's effectively a ratio of energy power used per unit of intelligence. And the idea is that certain tasks in terms of intelligence, such as compression, selection, and resetting, involve what are logically irreversible. This then incurs an energy cost by Landauer's principle, and that we can therefore measure effectively a ratio of the amount of energy it takes for a particular task based on the number of irreversible operations. And the point is that more irreversible operations lead to a higher thermodynamic cost and, in principle, make certain tasks less accessible. So, reducing irreversible operations reduces the thermodynamic cost for achieving the same intelligence score. So we're looking for ways to reduce the thermodynamic cost by lowering the number of irreversible operations. So what does nature do to solve this problem? Well, nature uses catalyst. Catalysis is nature's way of making otherwise energetically inaccessible transformations available. A catalyst works because its physical structure and geometry and shape in effect allow transformations which would be energetically unfavorable. So how does it do this? Its geometry and properties bind and orient the particular molecular configurations. This effectively, encodes informational structure in the molecule, and what it does is it creates a low energy pathway of intermediate states through which a reaction can proceed. Life would not exist and intelligence would not exist if it wasn't for the existence of catalysis. Because that structure persists and fits only certain substrates, it's reusable and selective. So the question is, can computational structures similarly determine which intelligent transformations are efficient? Can we use this idea to build intelligent systems? In this paper, I argue yes, that I propose this principle of algorithmic catalysis. It's the idea that that reusable computational structures which encode task class regularities, effectively shared abstract structure, can reduce the number of irreversible operations across intelligent tasks. By doing so, they can allow a pathway to perform the particular task. They can be designed in a way that can be reused, and they fundamentally are designed in a way that can be tailored to a particular task. These are these three principles. So the claim that I argue in the paper is that algorithmic catalysis provides a physical principle for understanding and designing energy-efficient intelligence. Now, there exists in computer science a field called catalytic computing, which some of you may have heard of or have done research in. The idea of catalytic computing is the concept of using a computational state without consuming it. But this area doesn't really consider the energy efficiency of doing so. So in catalytic computing, you may take a small space machine and it's given access to a much larger auxiliary or ancillary tape whose initial contents may be arbitrary. That machine can effectively use that tape during the computation as a scratch pad, but it has to restore it to its initial state before terminating. To these concepts in this paper, I add the idea of task class structure, adaptation cost, and restoration cost. The idea is to turn reusable memory into a model of energy efficient, intelligent computation. So what does an algorithmic catalyst do? So the catalyst encodes reusable task class Regularities, that's jargon for information which essentially helps you solve a problem in a way that helps constrain computation. So the idea of a catalyst is it actually eliminates unnecessary computational pathways, thereby reducing the number of irreversible operations. The gain of using catalysis as a principle comes from avoiding particular computations. I've tried to vibe code this in two diagrams here. We have a generic solver, essentially brute force, and then we have a catalyzed solve. So this is a particular use of an algorithmic catalyst which makes solving problems more efficient. Now, people will say, well, how is this different from just using an ordinary, clever algorithm? The point is that the catalytic form of sigma c here tries to do so by reducing irreversible operations. So that's the new thing here. And again, so sigma c is the catalyst. It describes regularities shared across a particular task class. I'm a physicist, so I'm into symmetries, for example. The encoded structure of the catalyst determines which successor states are compatible with those regularities, so that incompatible branches are discarded before they are explored. And this provides, in principle, a way for designing a tool by which we may improve solving certain tasks in a more energy efficient way. Of course, one of the challenges is exactly how you design the catalyst, which I don't really address in this paper. So future work. What are the results of the paper? I'll just sort of talk through briefly. So the first one is, well, how much can catalysis help? And so the sort of aim of this paper is really to plant a few early flags in the landscape as to, what the speed up produced by a catalyst may actually provide us. So the first result is that it's bounded by how much information it contains about the task class. So the speed up from catalysis here, so gamma t, is the reduction in irreversible operations on a task. Sigma c is the catalytic description of the abstract structure across the task class. Fundamentally, a catalyst cannot exploit regularities that it does not encode. And so one example I talk about in the paper is an F18 SAT problem. Encoding the F18 subspace reduces search from 2n to 2d. This is well known, but the sort of point in the paper is to show how this known result can be framed in terms of algorithmic catalysis and thermodynamic, energy efficiency. So a lookup table is not catalytic. It stores old answers, but it does not encode the rule needed to solve the next unseen instance. The idea is that a catalyst does this, and it does it in an energy efficient way. The second result of the paper is really around this question of what does structure cost? So encoding task structure requires a minimum adaptation energy, i.e. the cost for the structure to be physically encoded in the catalyst. E adapt is that cost. And this formula here, again, I can direct you to the paper, really basically tries to show that there is an upper bound on the adaptation energy. The minimum adaptation energy, and it sort of, if the information and the structure is already present, then the adaptation can reuse it. Otherwise, it has to be physically written into the catalyst. It's kind of obvious, but it just sort of makes the point. And then the third main result of the paper is, when is it worthwhile using catalysis? Well, a catalyst is energetically worthwhile only when the catalytic speed up gamma is worth the cost of constructing and restoring it in irreversible operations n star. So a trained model, database, index, or compiler is worthwhile if its repeated deployments effectively lower this adaptation energy. And catalyst compose, that's another result in the paper. So to summarize, this paper tries to present a physical theory of efficient intelligence principles via algorithmic catalysis. It aims to contribute to the principles for the design, construction, and reuse of selective structure. Intelligence requires physical work. Algorithmic catalysis is about trying to reduce the amount of physical work to perform a task you denote as intelligent. The design question becomes, which reusable structures can we obtain to achieve this. Reach out if you've got any questions. Thank you.